Okay, so all of the work that we did in the previous video leading up to this result where we get this Jacobian, all of this was intended to give us this approximation for delta A. So now we're going to see where this gives us a method for computing a double integral after a change of variables. So we are going to do what we normally do when we talk about Riemann sums in the context of double integrals. Again, remember the region that we're going to start with, the region that we're going to be integrating over to begin with is this region R. We're integrating a function f of xy over some region R in the xy plane. In our kind of general case here, we're just making it look like this little region. Now, well, actually, let me back that up. So in this case, the region that we're going to integrate over to keep this kind of general is this somewhat elliptical looking region right here. Just like how in type 1 and type 2 regions, we enclose a non-rectangular region with a rectangle. In the xy plane, we're imagining this sort of elliptical looking region as being enclosed by some other sort of general region R. And then the transformation T that takes us from the UV plane into the XY plane would take this elliptical region, which is surrounded by a rectangle, into this region here. So this ellipse right here, which can be any kind of region, I'm just, in this case we're just looking at an ellipse, maps to this blue region here, and the rectangle surrounding it maps to this more general region R here. Okay. Now, if we were to partition the region R into these little sub-regions here in such a way that if we trace each one back to the UV plane, we can find each one as the image of one of these sub-rectangles. Then this side, in the UV plane, this is set up for a Riemann sum that would lead us to a double integral. We would define, any part or any point, any point outside of this region, but still inside this rectangle, as giving us a value of 0 when plugged into F. That's how we dealt with type 1 and type 2 regions. Anyways, the idea is to look at the definition of a double integral as a double sum of each of these little regions here, f of xi, yj, where xi and yj are selected to be the lower left corner of each of these little regions. You can kind of see that point singled out right there, times delta A. That's the definition of a Riemann sum. If we take a limit, then that gives us this integral, but it's approximately equal to this double sum. Then if I make that change of variable, so xi is going to become g of ui vj. That's going to be the corresponding point here that maps to the point xi, yj over here. And then yj is going to become h of ui vj. That's just from the transformation itself. That's what x and y are supposed to be coming from. And then this delta A, here's the thing that we spent all this time working towards. Delta A we showed is approximately equal to this. Okay? The Jacobian times delta u delta v. When we apply a limit to this, the limit as m and n go to infinity, which is the limit as the number of these little subregions goes to infinity, then this goes from being an approximation to an exact value for that double integral. And so that leads us to this formula, or this technique for finding the double integral of a function using over a region R, using a change of variables. We perform the change of variables here. We plug in, here we're using x and y, x of uv and y of uv in place of g and h. It's just a different label for those functions. But if we have the conditions up here met, if t is a C1 transformation with a non-zero Jacobian, this term right here, And T maps S, this region here, into the region, or onto the region R here, where S is in the UV plane, R is in the XY plane. If we also suppose that the function f, the integrand, is continuous on this region R, and then in addition that R and S are both type 1 or type 2 plane regions. There's a lot of assumptions being made here, but in general you're not going to have to go through and check those assumptions. The examples that we work through, they're all going to be met just by default. T also has to be 1-to-1. It says except perhaps on the boundary of S. Again, that's not something we're going to have to worry about explicitly for the examples we look at. Then we can perform this change of variables here to evaluate this integral. So right now it's all very abstract. We haven't really done any examples yet, so we're going to try and make this more concrete with a couple of examples. The first thing I want to do is use this idea, the Jacobian, to justify the technique that we use for evaluating double integrals in polar coordinates. We've already discussed this, but in polar coordinates, the conversion formulas that we use are x equals r cosine of theta and y equals r sine of theta. Now remember, the Jacobian, which we're going to define, or we define this way. Normally I'd have down here a u and a v, but the variables that I'm changing to look like r's and thetas, so this is going to be an r and a theta here. Okay, remember this is a 2-by-2 determinant where the entries are the partial of x with respect to r, first variable here, partial of x with respect to theta, first variable here and second variable here. So these variables determine the rows, these variables determine the columns. Then I have partial of y with respect to r, partial of y with respect to theta. So I need to find these 4 partial derivatives from these conversion formulas. Partial of x with respect to r, let's do that. So with respect to r, that would be cosine of theta. Partial of x with respect to theta would be negative r sine of theta. Okay, partial of y with respect to r would be sine of theta. And the partial of y with respect to theta would be r cosine of theta. Okay? So, using those values in our Jacobian is going to look like this. R theta equals the 2-by-2 determinant, cosine of theta, negative r sine of theta, sine of theta, r cosine of theta. Okay. Multiply these two, that becomes r times cosine squared, so r cosine squared of theta, minus these two squared, that's negative r sine squared, so minus minus, that makes plus. Okay, factor the r out, it becomes r times cosine squared plus sine squared, which is 1. This is just r. So our Jacobian gives us r. Well, if you think about how we evaluate a double integral over some region r of f of x, y, dA, if we want to evaluate that double integral in polar coordinates, so over some region S, which describes the same region but using polar coordinates instead of x's and y's, then I would make the appropriate variable substitutions. I do f of r cosine of theta, r sine of theta. The dA is supposed to become our Jacobian times dr d theta, but our Jacobian was r, so we get r dr d theta. And that's exactly what we talked about back in 10.3. That's how you evaluate a double integral with a change of variables into polar coordinates. So this shows that the Jacobian is giving us this correct factor of r that we're supposed to be getting using that conversion to polar. But the benefit of now, keeping things more general is we can do all sorts of variable substitutions, and the Jacobian will tell us what this little factor here is supposed to be to give us correct answers. So let's try another example. Now, most of the examples you're going to see in the homework are going to give you a double integral to evaluate. They're going to say, evaluate the double integral over some region R of whatever the integrand looks like. And R is going to be described in some way. And then they're also going to give you the change of variables. They're going to give you the transformation that they want you to use, and then have you proceed from there. The reason for this is because in double integrals, oftentimes it can be really difficult to determine what the best change of variables should be. But I wanted to do an example where we don't know ahead of time what the transformations should be and see if there's a logical way to come up with them. So here, I'm going to start by looking at this region R by graphing it. It says it's enclosed by these 4 lines right here. So let's graph this. All right. So the line x minus y equals 0, that's the same thing as the line y equals x. That's it right there. X minus y equals 0. And I'm not worrying about being super accurate because this is just to get a general idea of what this picture looks like. X minus y equals 2 would actually give me a parallel line to this one, but it's going to have a y-intercept of -2, x-intercept of 2. Again, not worrying too much about everything being perfect. X minus y equals 2. All right, x plus y equals 0. That's the same thing as y equals -x. So we're going to get a line that looks like this. This is the line x plus y equals 0. And then x plus y equals 3. That's going to give me one with a y-intercept of 3, but parallel to that line. So we're going to get something that looks like this. This is the line x plus y equals 3. So the region R is this one. Now mine looks more like a parallelogram, and that's because, again, I wasn't being super careful about making my lines perfect. But you can show that these lines, for example, x plus y and x minus y, have slopes of 1 and -1, or -1 and 1 respectively, I guess, which are opposite reciprocals of each other. That means that these lines here are perpendicular to these lines here, making this a rectangle. Not that important, but I just wanted to point that out. We did an example before where we found a region in the UV plane that was rectangular, and a transformation that took that rectangle to a region kind of similar looking to this one. Our approach to that was to take a look at these expressions. Notice that all of the equations for these lines are given in standard form. So again, x plus y appears in 2 places. X plus y equals 0, x plus y equals 3. We know that in this region R, if I put any other lines that are parallel to these two and between them, they would be of the form x plus y equals some constant between 0 and 3. So that means for any point in this region, x plus y is between 0 and 3. Similarly, using these two equations, I could say that x minus y is between 0 and 2. Like this. And this suggests what I should use for my variable substitutions. It would make sense to have u. Actually, I think when I did this before, I swapped the two. So I'm gonna call this one u and this one v. I'm gonna call u x minus y and v x plus y, and you can call it either way. It doesn't really matter. I'm gonna say let u equal x minus y and v equal x plus y. So now Rewriting these with the correct substitutions, I can see that u is between 0 and 2, and v is between 0 and 3. Okay? Now, if I want, so what that would do is give me this region down here. Draw this here in the UV plane. It's the rectangle where u goes from 0 to 2, v goes from 0 to 3. So I would be calling this region S, and what we want is a transformation that takes S to R, maps S onto R, okay? So that transformation is going to be defined as functions of u and v that give me the x and the y respectively. In order to come up with those, I needed to treat this like a system of equations like we did in that previous example and solve for x and y in terms of u and v. So if I set these up, u equals x minus y, v equals x plus y. If I add, I get u plus v equals 2x. The y's cancel. This leads me to x equals u plus v over 2. Similarly, if I were to try and cancel the x's, so for example, if I did this equation minus this one, v minus u, then these x's would cancel. Y minus negative y is 2y. And this leads me to y equals v minus u over 2. These define the transformation t that takes this rectangle, S, into this, also a rectangle, but the sides are not parallel to the x and y plane, so it's not one of the easy types of rectangles to integrate over. Okay? I'm running out of time on this video, so in the next one we'll take these transformations and use them to evaluate the integral we're being asked to evaluate.